I want to share a tale before I begin. I've given several talks before, but I've never looked at my own recording. It's because it's just too awkward to watch myself talk. But today I clicked open one of my recordings because of this whole other story about how I realized this morning I deleted my slides for today, and I had to rework everything again. And then I realized that while I was watching the recording, I realized that I say so many when I'm presenting. It was really painful to watch. So the takeaway is that if anyone is presenting in the future, it is extremely helpful to record and watch yourself first if you haven't already. Another takeaway is I'm going to say a lot of today, so please bear with me. All right, with that, my name is Jenny Shih, Shi Jinghua. I work at Shopify and I am from Taiwan, but I moved to Toronto, Canada later last year, and it's been cold. Another random fact about me is that when I come across something interesting, I sometimes get too obsessed and make a talk out of it. So, like functional programming. So the hype is up for the topic. Here's an article from GitHub reading project last year that talks about the rising of functional programming over the past decade. Even though the term has become popular, there are still some common conceptions about functional programming that might be misleading, like you have to dig math and be able to explain monad in 2 minutes. But I want to explain in the, Ruby developers term what functional programming is, and even more relevant to us, why should we care about it? The main point I want to convince you today is that functional programming helps us write better Ruby code. To properly understand what functional programming is, let's first talk about programming paradigms. It is a way to classify programming languages based on their features. So oftentimes you hear people say Ruby is an object-oriented language because a lot of its concepts are based on the object-oriented paradigm. And the functional programming that we're talking about today is another programming paradigm. And let's look at the mental model to ease our way into understanding that more. For every program, we can break them down into 3 components: value, behavior, and time. What does that mean? Say, today we have a program that has this expression, puts hello world. In this example, puts is a behavior, hello world is the value. In another example, we assign WMBRB to the variable faith group called upcase on it. Thus, the value of the variable is now different in different execution point. So we see the time element in between those 2 expressions. To look at our mental model again and try to use the 3 components to an object-oriented program, it will look something like this. The time element is within both value and behavior because they can both those 2 components can change over time, and they are all encapsulated into object. And we'll have multiple options. So while each having the same arrangement of those components. If we model functional programming with the same 3 components, we have 3 distinct circles. So now let's look at them one by one. First of all, value. To talk about value in functional programming, we need to talk about the concept of immutability. And the not overly complicated definition of it is don't change a value once you initialize it. In Ruby, it would be like adding the method freeze on objects, like this example. And also in class definition, we will discard the attribute writer and attribute accessor on the instance variables, because having them means we're giving open access to modify the values of the instance variables, and we don't want that. And why would we want immutability? From a developer's point of view, it is a lot easier to reason about the code if you know that there's a guarantee that the values cannot be changed. As an example, we define a struct called flight with an attribute date. And I initialize my flight variable with a certain date. And then I share this value with another variable called friend's flight. Later, the friend's flight changed its date to a day earlier. And now when I expect my flight, I will see that the date of my flight has also been changed. That example was a rather short one, so it's easier to spot the mistake. But normally we'll be working with a much larger code base where a variable can easily change values across different files. And it will be painful if a bug happens in one of those intermediate value states of the variable. And the second reason is that is from the runtime's point of view. Without the need to worry about a value and if it will be changed later or not, it can be a lot easier to support concurrency, which I will talk about more in details later. Okay, so next question would be how. First, a new data structure called data is just released in Ruby 3.2. This is the PR that introduced it. It aims to be a simple, immutable value object. So instead of using class or struct to define our object, we can now use the data class, and the guarantee of immutability will just come out of the box when you use it. If you are not on Ruby 3.2 yet, but still want to try out this idea, there's a gem called JStruct that does the same thing for you. It is JStruct is part of the Dry Ruby collection. You can visit dryruby.org to find out more. There's a lot of functional programming ideas in the collection, not just this one. So definitely check it out if you want to dig more into functional programming and how it's realized with Ruby. So that concludes the value part of the functional programming paradigm. The core idea of it is immutable data. Next, we look at behavior. The key idea here is pure functions. And a pure function is defined in two conditions. First, it only depends on its input argument. For example, this function is not pure because there's not input argument, but it relies on the time module to produce a value. So you'll be different every time you call it. And if we change it a bit, and instead of calling a time module right inside the definition, we can pass the timestamp instead from argument. Then it's a pure function because as long as the argument is the same, the result will be the same. The second condition is that it does not mutate states. That is, it has no side effects. So this is not a pure function. Although it satisfies the first condition, it has changed the variable stir forever by appending 2 exclamation marks to it. If we change it to this, then it's a pure function because it doesn't modify the stir itself. As to why, I will read this quote. The problem with OO languages is they've got all this implicit environment that they carry around with them. You wanted a banana, but what you got was a gorilla holding the banana in the entire jungle. And this quote is by Joe Armstrong, creator of Erlang, functional programming language. I will highlight the word implicit environment here. I think the analogy captures the essence of why pure function is a good thing. So here is an effort of illustration. Suppose the orange circle is our brain. And if we don't have pure functions, that means when we look at a function, in this case, the banana, we can't just focus on that, but also need to pay attention to a lot of other parts external to this function, because if we don't do that, we may find ourselves missing certain key aspects of the function, or would be modifying some state somewhere else that would have some effects down the road. And that would be that can be overwhelming. On the other hand, if we are able to focus on the function as it is, would have more brain space, focus on the details of the function itself, and thus more likely to reduce bugs. It will also give us a much easier time to write the tests, because pure functions are by definition isolated. And you also give the reviewers, the PR reviewers, an easier time, because now your PR is so small and neat. So it's basically a win-win, win-win situation. With that, how do we do that? The first technique that we can use to produce pure function is parameterization in functional programming's term, or dependency injections in object-oriented term. This is an example. This is a newsletter class, and we have a subscribe function. First, inside the function, we first check some conditions. Return false if those conditions are not met. And if they do pass, we add the email to the mailing list and return true. There are some traits that make it not pure. First, we are calling an outside module to do a validation for us. We're also relying on the instance variable mailing list that is a state that we have no control of. To fix it, we can move the two things to the parameter list. Now we don't rely on implicit knowledge of the outside world for this function. But there's still a thing that makes it not pure. In this operation, is modifying the state of mailing list. And that brings the second technique, transformation instead of mutation. Instead of relying on implicitly modifying the mailing list, we can just return the new array as a return value and preserve the original value, like this. Now, if we pass this newsletter class to the two conditions, only depends on its input agreement check, does not mutate states check. So that's the behavior part of functional programming. The key idea is pure function. The last component is time. And this is where we talk about concurrency. As we've seen before, this is how I think about an OO program in my head. And if we try to run a Ruby program concurrently out of the box, we cannot. There's this thing called the global interpreter lock that prevents Ruby code from doing so. And the reason that we need this lock in the first place is threat safety. That is, there's a risk in messing up the timeline of object mutations, thus messing up the program itself. And functional programming is quite good at handling this, because it separates the time element out of the value and behavior, which makes concurrency easy. Take Elixir, another functional programming language. Take Elixir's concurrency model as an example. It uses this actor model. So here we define a process or an actor as a unit of execution. They can run concurrently, and they will try to communicate with each other. They can only communicate with each other by sending messages instead of mutating the states of each other. And this is what it looks like when running with multiple threads. And one reason that Elixir is great at this and can easily achieve this state is that it doesn't need to worry about the states problem, and it doesn't need so it doesn't need a lock like Ruby does. in recent years, Ruby has also started to build its own concurrency abstraction. It's called Ractor. Mats itself said so that it's very important. This is how we can understand Ractor. A Ractor is also a unit of execution. But what's different with the Elixir model is that each Ractor contains multiple threads, whereas a thread with Elixir can contain millions of Elixir actors. And each Ractor has a clear boundary and its own interpreter lock instead of just one global lock. So now the Ractors can run concurrently of each other while still guarantee that the code inside each Ractor is run sequentially. And as of Ruby 3.2, Ractor is still flagged as experimental, but it's very exciting to see its development in the future. Okay, and that concludes the 3 components of the functional programming. To recap, functional programming has three components. We looked at the value and the importance of immutable data. We looked at the behavior and the importance of pure function, and how with the separation of time we can achieve concurrency. With that, I hope I've convinced you that by borrowing those ideas from functional programming and incorporating into our Ruby code, we can write better and more maintainable Ruby code. Thank you. The rest will be resources. Feel free to check it out if you're interested.